Alright everybody, this is a video where we're going to go start to finish how to do a PCB. So before I'm going to try to do the whole thing. I always hate it when people say, oh, here's how you do it, and it starts off with like, oh, this thing isn't installed, but I installed it beforehand. So we're going to even go through the process of installing all the software as we go through here. There's a couple places where you're going to have to log in or create an account when you do this. I'll tell you where those are and we can move forward. But to start, let's install the software, and then while the software is installing, we'll sort of talk about the strain gauge amplifier. So the software we're going to use is Easy EDA. This is a free software used for making PCBs. This one is particularly nice when you're using the Chinese fabs and when you're using the Chinese parts suppliers. So LCSC is the parts supplier that's affiliated with Easy EDA. And LCSC is sort of like the big DigiKey of China. There's also JLC PCB, which is what we'll be using for actually fabricating these PCBs. I'm going to try to take you really through all the steps that you would need to do anything with a PCB design. But there's lots of different EDA softwares available. EDA stands for Electronic Design Automation. It's basically just a tool that allows you to symbolically represent electronic components in a schematic, and then it translates those schematics to the physical layout. So it does that by connecting the physical pins and the physical footprints for a component, for a chip, to the symbolic pins and symbolic connections. And so the whole thing is it makes it less likely that you're going to make a mistake. You could theoretically draw out a circuit board design and draw every little pad and try to make it all correct. But if you segment the problem and break it into little tiny pieces, you're much more likely to have it work out successfully. So that's why we use these EDA softwares. So easyeda.com is the website here. I have an account. I created an account to do this. And so probably when I log into this account, it'll be sort of affiliated with my login. You can it's free. You can create an account, and you're going to want to download this. So we're just going to download this software. We're going to do the Intel AMD. I hope I have a 64-bit processor. I'm using this on a clean version of a computer, so I'm not quite sure what version I have. Let's install this though. And there's several of these software tools you can use. Some other really good ones, probably one of the most popular one is KiCad. KiCad is software that, I'll just do this offline mode. But KiCad is another popular one. KiCad is a little bit more full-featured than this. What I like about Easy EDA, and in general with these software tools, is don't get more of a tool than what you need for what you're doing. So there are very advanced EDA software packages. The ones by Altium is one that we've used in our program. We don't quite use it anymore because it was a little tough to do with a lot of students. But the more advanced you get with the software, the more the software is capable of doing things that you really want. If you worked at a big enterprise, if you worked at like a Tesla, or you worked at like Apple or something like that, you'd want to use one of these big enterprise EDA software tools. And those really let you do the types of things you have to do in a big company. Things like thermal verification, things like noise verification, things like collaborative things, right? If you're working on an iPhone and you make a change to an iPhone circuit, there's no way Apple's going to allow a single engineer to make a change to the iPhone design without it being checked by 1,000 people. So those other software tools allow you to do things like you make a change and then you say, okay, this is what I want to do, and then it goes through a certain levels of authorization and verification, and then it finally becomes part of the design. All those features are nice, but they add extra steps, right? They add things, they clutter your view, they just add things where you're like, am I supposed to do this? I'm not quite sure. It's better if you don't need those features to just stick with a software that doesn't use them. So, and that's the easiest. Same with like word processing, right? If you use Microsoft Word, most of us use about 5% of the features of Microsoft Word. And Microsoft Word is really good about, it only shows you the buttons that it thinks you're going to use, right? So a lot of software has done this in the last 10 years or so. They've really gotten good at, they don't show you an icon unless they think you're going to want to use it. And so people who are doing who are using extra features, people who are doing, if you're trying to do a Word document and you're trying to mail merge it for an email, there's going to be a whole set of tools that you would normally never see as a normal user. Same thing with the EDA software. So we're just going to skip that. Okay, so it's going to try to take us. I'm going to skip this because I'm going to take you through some of this stuff. But this is the software. The software is installed. What I like about this software is it has a limited library, but the library is all the stuff that you can get at LCSC. So LCSC, again, it's a fairly big website. If we go here, we can go to, I think I have LCSC open here. So if you go to LCSC and you just search, I think HX711, we can find, this is the strain gauge amplifier that we're using. So this is for sale on this website. This is actually where I bought it from. You can see these strain gauge amplifiers. If you buy 50 of them, they're only 40 cents each. And the circuit that we're going to make is based on this strain gauge amplifier. And if you go here to SparkFun, you can see this circuit, which basically just consists of that 40-cent chip and 2 capacitors. This sells for $11. So that's what I was talking about in class about. Sometimes it's beneficial. Sometimes it's actually cost effective. It's not time effective, of course, but sometimes it's cost effective to build your own thing. It's not the sort of thing where you have to be selling a million of these for them to hit a price point. There's a high markup on a lot of this stuff, and a lot of people just don't realize it. So, so we have the software, the Easy EDA software installed. That's a fairly painless process. Just to get us a little bit further, let's start a new project, and I will call this strain amplifier. Okay. So when we create a strain gauge amplifier, of course, it's showing us all these tips and hotkeys, and those are probably good if we're going to use this software a lot. I don't know this software that well, to be honest, so I'm going to skip that, but this is our main sort of schematic sheet. So this is where we're going to put our symbolic components to build our circuit. If we want to, we can change the name here. We can do strain gauge amp version 1.0, your company, www, and the date's fine. And we can do drawn by, oops, maybe we can't. Maybe we have to specify that somewhere else. Document setting, oops. Okay. Well, there's a way to, I haven't messed around with it enough to see how to do that. But you can add the draftsman. So typically with this sort of thing, there's, in a big company, there's going to be a draftsman who's going to do the schematic, and then there's going to be an engineer who's going to do the hardware layout. So a lot of times you can design a circuit in a schematic, but there's things you need to know about how to physically structure that circuit that are going to matter. So for instance, if you have a USB connection, the USB data lines are very high speed. You can't just run the wires however you want across the board. They have to be kept close together. They have to be kept over a ground plane. There's a lot of rules for that. The person doing the drafting might not necessarily know those rules, whereas the person doing the PCB might. In your case, in my case, we're going to be doing both the schematic and the PCB. So if those things show up, it's on us to know. But when it comes to, like, say, drawn by here, that's referring to, at a big company, there would be a difference possibly between the draftsman doing the schematic and the person doing the board. Okay, so what are we actually going to build? So this is our where we're going to start is with this schematic here, and what we're going to build is this. So what I like about SparkFun is open hardware. So they have to be open hardware, they have to include the design files for their designs. We're basically going to copy this design. And so we're going to go to documents, and they show us their schematic. Now their schematic was made using a different piece of software than ours, but it's fine. So this schematic shows they have a strain gauge amplifier, they have a couple capacitors here, they have some resistors, they have an inductor here, and we're going to talk about what all these things are as we go through it. But this basically gives you, this is the schematic of the circuit that they built. So they sell the, what they sell is the board here. This looks very different. This board looks very different than the schematic that you see here. But the schematic is quite a bit easier to understand, right? You can tell, oh, okay, I see this is a transistor here. And I can see, oh, this is a capacitor and this is an inductor. If I'm looking just at a circuit board, this computer's slow. If I'm looking just at a circuit board, you know, these are just clumps, right? They're just chunks. They're just rectangles. I don't necessarily, I could guess, right? Well, you know, but this is just a black chunk here. Do I know that this is a ferrite bead or an inductor? No. I do know that from the schematic because I can see how it's labeled. These I would guess are capacitors, but it's only because I've been doing this for a long time. It's not as clear what's going on in the circuit from the physical board. It's much more clear from the schematic itself. So we're going to start with the schematic. We're basically going to copy this. But before we do that, let's look at the actual data sheet for the part we're looking at. The strain gauge amplifier, the HX711. The data sheet for it is right here. So this is the data sheet. So this is a 24-bit analog to digital converter. We talked about what that means in class. That means there's 24 bits of resolution on the analog measurement. That's a very high resolution analog to digital converter. How do they do it? How does it do this? I believe it's a sigma delta. I'm pretty sure it's pretty much got to be at that higher resolution. And we talked about those briefly in class too. But the main thing we're going to look at, if this is the main chip we're going to use, if we decided this is our strain gauge amplifier, we're going to look at kind of the first couple pages of the data sheet, and we're going to say, okay, what's their typical design? A lot of times they'll show, here's a typical circuit that we build, and you know, they'll say this is, and the nice thing about this is looking at this sort of a thing out of the data sheet, make sure you don't miss something obvious. So a lot of times they'll say, hey, for this thing to actually work, you have to connect a capacitor to this VBG pin. Would I have known without pouring through the data sheet that you have to connect a capacitor here? No. So there's some details in a circuit that don't make sense unless you look at the data sheet. Now let's compare the two. Let's look at this and the other diagram. So first of all, supply voltage, this transistor, this set of resistors. So we have the supply voltage, VCC, we have that transistor, we have this set of resistors. So they have kind of the same, is there this capacitor here, this C2? Nope, I don't see it on here, so it looks like they added some extra little things, which is fine. But you can see they kind of match up a little bit. And so normally the first place to start when doing a design is look at the data sheet for the part, look at the schematic. There's a lot of details of this that I'll talk about, but some of the details of just knowing from scratch that you'd have to do that is something that you get from doing a full like 4-year, actually probably from working for a year or so in a company after you get a 4-year degree. So if some of the stuff, if you look at it and you say, well, I don't know why we did that, it doesn't necessarily, you know, it's some of these things are just, you don't necessarily know what you're doing or why you're doing it. When I look at this, I'm like, I could guess why they put this inductor here, but it's a design decision that, you know, unless you're active in designing for these sorts of amplifiers, you might not know. So actually, I think this capacitor is there, actually. It's just wired funny. So VBG to A ground. Yeah, okay, that's this capacitor down here. So they did put that capacitor there. They just sort of show it a little bit differently. But once we sort of see some examples, once we look at the data sheet, once we get an idea for kind of the circuit we want to build, we can start piecing this thing together. And we're going to start by piecing it together in the schematic. So let's start over here and let's get this main chip in there. So the HX711. Now I know we're going to have this. This is one of the main reasons I'm choosing this software is because all the parts are ready for us. We don't have to build any parts ourselves. We might have to if we used a different software. If we used KiCad, which is another popular free software, we would have to import this part. I kind of wanted to skip that, so I'm just going to use Easy EDA. So let's go to the library, and it was HX711. And yeah, so we searched for it and we found this part. So, and this kind of hidden over here, but if it shows, there's a, right, yeah, so verified and assembled. So these two buttons mean, the assembled means if you want PCB assembly service from JLC PCB, this part is available for assembly service. So it means if you ordered this board from them and you said, I also want you to put the parts on the board, solder and memory, everything like that, this is a part where they are willing to do it. They'll charge you for the part. You'll have to buy the part. But they are willing to do this assembly service. And that doesn't matter for us. We're going to be assembling them by hand. But for us, we're just going to click on it, and then we're going to click place. And then we're going to put it somewhere in our schematic. So we'll just, this is kind of central to the circuit, so we'll just kind of put it center in somewhere. We'll hit escape to start, because otherwise it's going to have us place a whole bunch of them. For this board, I think we just want one. If you want multiples, I guess you could do a board with multiples to have fun, but let's just do that. Okay, so now let's go. There's a lot of pins here. These don't make a lot of sense. They're kind of random terms, so let's go back to the data sheet. So what's happening here is they have VSUP, which is voltage supply, and they have DVDD. So a lot of times what this is quite often you'll have a circuit where there's two power sources. There's a power source that powers the digital communication side, and there's a power source that powers the analog circuit side. There's two main reasons for that. One is quite often the digital logic levels will be a lower voltage than the analog voltage levels. So for instance, if we wanted to power our strain gauge with 5 volts, but we wanted to have it communicate with a microcontroller that was running at 1.8 volts, we would have to specify 1.8 volts for the, well, this can't do 1.8 volts for the logic. Let's say our microcontroller was 3.3 volts. We would have to specify 3.3 volts for the digital logic and 5 volts for the strain gauge. And then it would do the analog stuff with 5 volts and it would do the digital stuff with 3.3. In this case, we're okay. We're all using 5 volt microcontrollers. We're okay powering both the analog and the digital with the same supply. Another reason you want to separate these two is digital supplies are often very noisy. Digital circuits switch, they have a clock. Every single clock cycle they're switching. That switching creates a lot of noise, and so sometimes you want two separate supplies. So the analog stuff that's very sensitive, and this is very sensitive, 24 bits of precision on an ADC is going to be very sensitive to noise. If you want to keep those supplies separate to avoid digital noise, wandering over to the analog side, that's another reason why you might do that. For us, we're just going to make these the same supply. So we're just going to have power. So in this SparkFun circuit, they have VDD and VCC, which is it's referring to the digital and the analog power supplies. This terminology is, I don't want to go over why they're called VDD and VCC, but basically it refers to the two different types of transistors, the MOSFETs and BJTs. In this case, it's going to be the same. So for the SparkFun, they said, okay, you can provide two different powers. If your strain gauge is powered by a different voltage than your digital, you have two digital pins and you have a ground reference. There's almost always a ground reference in these cable bundles. And this little symbol here, this J1, this is an off-board connector. This is what students a lot of times forget when they're building a PCB. If you need to get signals onto a circuit board and off a circuit board, the physical pins that you solder on or the physical wires you solder on have to show up somewhere in your design. They have to show up as some kind of a symbol that's a part of the board that gives you something to solder to. Quite often we have students that do their senior projects or something and they have a signal and they see the signal on the schematic, but they don't actually provide a way to get that signal off the board, so they have no way to connect to it. Okay, so for us though, we're just going to power this with the same supply. So let's go back to here. So VSUP, VDDD, so these are pins 1 and pin 16. The pins normally you start at the top left corner. You count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this would be pin 1, this would be pin 16. It doesn't show up on the schematic. I prefer to always have the pins show up on the schematic, but it doesn't in this case, and that's fine. So we're going to power these by the same thing. And to do that, we're going to go to component library. We're just going to use VCC. There's a drop down. We could choose a whole bunch of different labels, but VCC is fine for us. So we're going to put VCCs on both of these. We're going to use the same voltage and then hit escape. Let's go back and see here. So this is also, look, they have a little fancy little thing over here for the rate. So they say default close, data rate set to 10 samples per second. Open jumper set to 80 samples per second. So basically this pin for rate sets the rate at which it acquires the signal from the strain gauge. And there's two speeds, 10 samples per second or 80 samples per second. 10 samples per second is slower, but it's going to be more accurate. The question you want to ask yourself is, for something like this, is 10 samples per second okay? When would it not be okay? 10 samples per second might not be okay if you had to quickly sample a strain. So if you're sampling a bathroom scale, 10 times a second is probably more than enough. The person's going to be standing there for a long time, But if you're sampling a rotating spindle, let's say you have a spindle on a milling machine that's rotating, you might have to sample a lot faster than 80 samples per second, right? If that thing's really spinning and you have an oscillation, if the rotation is more than 80 RPMs, or if it's more than 10 RPMs, you're going to need more than 10 samples per second to actually get a real changing strain reading off of that spindle. But for us, 10 samples per second is okay. So rather than build this circuit, we can probably just leave this closed. So if this is closed, this rate pin is connected to ground. Let's verify that in the data sheet. So where's the rate pin? Yeah, so they just ground the rate pin in this example. So let's just ground it. We don't need to make ours as fancy as the SparkFun one. If you want to, I guess you can. So we're going to use the ground supply flag here for the rate. We'll leave a little space here. Hit escape. Now, I didn't put the ground. A lot of students do funny stuff. I'm going to hit R to rotate. So I hit the R key. A lot of students will do stuff like this, and they'll kind of cram parts in really close. I prefer not to. Give it a little space. There's no reason to have this too crammed in. So leave a ground pin there. If we click on this pin and then click over here, we draw a wire. So what I like about Easy EDA is it's very nice for connecting wires because you just click and click, and it knows. Yeah, you're probably, if you're clicking on a pin dummy, you're probably trying to to do a wire. So, all right, let's keep building this out. Oops. So if we go to X in, so this is a crystal oscillator. These X in, X out. These are for you to connect an external crystal oscillator, which you might want to do for whatever reason if you want a more accurate timing or something like that. In this case, they ground it. Let's go back to the data sheet. They also ground X in and leave X out floating. So we're going to do the same thing. We're going to ground X in. So there's a couple ways to do it. We could connect another ground symbol, or we could just do this. So if we wire this pin to the same wire as ground, both of these pins should now be connected to ground. The X out pin, we're going to leave disconnected as shown here and shown here. But we don't normally just want to leave a pin disconnected. If you leave a pin disconnected, the software is going to say, hey, you got to connect that pin to something. So I think I don't quite know, but I think if we can place a no connect flag like this, boop, we're going to place that on the pin, hit escape. That tells the all that does is it tells the software, hey, I know I'm not connecting this pin. Don't worry, it's okay. I'm supposed to do that. Okay, data out and the clock pin, these are connected to so these are how we communicate the data back to the microcontroller. Those have to be connected to this off-board header. We'll do that a little bit later. NB plus, NB minus. So it turns out this strain gauge amplifier actually has two channels that we can use, in A, in B. If we look at the SparkFun one, the B channel, it has a little jumper for it, but it doesn't really use it. It gives you access to it, but it doesn't really use it. We're only going to be measuring one strain gauge for our project, so we don't have to connect this at all. We can just ignore NB plus and NB minus. If you want to on yours, if you want to do what they do here in Osh Park, you can. If you want to make yours more full-featured, give yourself more options to measure 2 strains or something, that's fine. You can do that if you want. Okay, so then what do they have here for this NA minus NA plus? So they have a capacitor between these. That's fairly common for filtering the noise. So quite often you'll put a capacitor between, if you have a signal that you don't want to be susceptible to noise, if it's a differential signal as we have here, putting a capacitor between there is a good way to filter out that noise. But to really get an RC time constant filter, you also have to have resistance on these lines. So they have resistance here coming in that's 100 ohms. Now a lot of students think if you put a 100 ohm resistor in series with this signal, it's going to cause a voltage drop. But the inputs to these amplifiers, one of the things we talked about in class is with strain gauge amplifiers, with differential amplifiers, the current flowing into these terminals should be 0. It really should be 0. So the inputs here are normally the inputs to, the direct inputs to an op amp. So the assumption that there's no current flowing in is actually very good. So putting these resistors here really only has the effect of low pass filtering this. It doesn't, it's not going to cause a voltage drop across here for the signal because there's going to be no current draw. It's only going to cause a low pass filtering. So let's build this. So as we build this, we are going to choose capacitor values. This is where you have to know what things you have to work with. So the 0.1 microfarad capacitor, we have 0.1 microfarad ceramic capacitors that are meant for mounting surface mount components. But the size for everything in our library that we have is 0603. So 0603 size means it's 0.06 inches by 0.03 inches. You have to be careful though, because the sizing of components is also metric. So 0603 can also mean 0.6 millimeters by 0.3 millimeters, which is quite a bit smaller than 0.06 inches by 0.03 inches. So we're going to have to be careful as we choose this part. So let's look for this part. So let's just do capacitor US. Yeah, so 0603 is already selected here. So 0603 US, I don't fully trust it as listed here. Another thing we could do is we could find a capacitor that's the value that we're looking for. So if we go to library and we search for 0.1 microfarads, will that give us any capacitors? Yeah, now we want to be careful to make sure it's the right size. So this capacitor 0603, so this capacitor might work. If we want to check, it looks like this is going to work for us. One thing we can do if we want to check this is we can, well, let's place it. Hit R to rotate. It's going to be about here. But if we go back to the library, I think we can find the LCSC part number. Maybe right click and go view data sheet. What does that do? Yeah, so this is the part. So if we check the data sheet for this, oops. Well, no. But one thing we can, well, we can't do it here either. I'm guessing this is 0603. I did this once at home and I didn't run into this issue. I'm guessing this is 0603 Imperial. But we'll sanity check afterwards when this part gets placed, because you can definitely visually see a difference between 0603 Imperial and 0603 metric. Actually, I'm a little worried about this. I'm a little worried that it just says package 0603. Let's download the datasheet. We'll download it. Okay. So 0603. Yeah, they're just saying 0603. They're not saying, based on the sizings they have, this field, oh wait, right here. Oh, no. Well, let's assume it's going to work. Let's assume it's going to work. Okay, so that's our 0.1 microfarad capacitor. Now we have to go back to here. Let me just make sure I'm still recording. Yeah. So back to our SparkFun example, we have these 200 ohm resistors. So let's go back to the library. We'll just do, I like it when they just show, let's try searching for 100R. See, you got a lot of inductors that are 100 ohms. See, this is R0805. That's not the right size. R0603. 100 ohm. Okay, that should be fine. So with resistors and capacitors that are this size, it doesn't matter if we use the exact same part. The footprints should be the same. So an 0603 resistor is an 0603 resistor. The specific brand you use ultimately doesn't matter. Or, I mean, it might matter. But in this case, as long as we find a part that shows up the same in the schematic, in this case, 100 ohm resistor, and it has the right footprint, we're good to go. So let's just place that. So we're going to place one here, and we're going to place one here. Oops, hit escape. Move that back here. And so those have to be wired up. So we'll wire these like that, and like that. Oops. So now when I say we'll wire these up, we're not actually wiring these yet, right? This is wiring them in the schematic. This is telling the software how these things are connected together. Ultimately, we're going to have to wire them together in the circuit board itself too, which we'll get to a little bit later. Okay, so then these 100 ohm resistors go directly to our breakout on the other side. So if we look at the actual SparkFun PCB, you can see there's these wire solder points. We could solder headers or we could solder wires directly here. But there's ones on this side where we get power and ground and we communicate with the microcontroller. Then there's wires on this side where we connect to the strain gauge. And so those symbols that show up in the schematic, those symbols are right here. So these are the two little connectors that make those little holes in the board on each side. And we're basically going to copy this. Well, we're going to fix it a little bit. So let's add these other components though before we get too far. So this analog ground capacitor. So analog ground. Okay, so there's analog ground pin which is grounded, and then the band gap reference capacitor. So what this is doing is internally this chip is generating a reference voltage. Every analog to digital converter needs to have some known voltage to compare to. And in this case, they're producing a known voltage to compare to by using the silicon band gap. That's the potential energy difference between the two bands in a semiconductor material. For silicon, that's normally going to be about 0.7 volts. Sometimes these band gap references are closer to 1.1 volts. It depends on the actual process technology they're using. But it's normally a very precise known voltage value. So it's an easy way to make a voltage. Effectively, this band gap reference is saying if you have a diode and you run current forward through a diode, you're going to get that diode voltage across it. That's what it's using to generate this voltage. The reason you have to have a capacitor here is because you want that voltage to be smooth. You don't want there to be any noise. If there's a little bit of noise in the supply or something, you don't want that to show up in your reference signal, because if you're comparing an analog value to a reference that's noisy, your data is going to be as noisy as that reference or that signal. The worst of both is it's going to get. So we put this capacitor to smooth that out. So the DigiKey or the SparkFun schematic, you can see they have one ground, which grounds the analog ground pin, and then they have a capacitor that's on that same ground side, which is the VBG, and they have that same ground being used as the reference of this divider. If you look back at the data sheet, they're basically this ground, and this ground. All three of those grounds are using the same symbol in the SparkFun one, but it is wired up the same. It's just a little bit confusing. So let's put this 0.1 microfarad capacitor in there. So we already have a 0.1 microfarad capacitor here. Oops. So what we're going to do is click it and hit just Control-C, Control-V. We're going to give ourselves another capacitor. So this one is so this one's going to be for the analog ground. This might get a little messy. What we might want to do is we might want to select all these. Oops. Oops. Well, that's not good. I don't know why I did that. Wow, this is lovely. messed up. Oh, this is going great. I'm using the scroll wheel to, oh my god. Okay, well, finally got that figured out. Oops. Oh, okay. I'm gonna put this capacitor back here. So the one side of the capacitor, well, let's do it like this. One side of the voltage band gap pin has to be connected to this capacitor. The other side of the capacitor has to be connected to ground. So we can either place another ground or we could just hit this ground, Control C, Control V. And that's ugly, but it'll be fine for now. The analog ground also needs, now you can see why they reuse this ground, because the analog ground also needs to be grounded, but let's just press Control V again. Let's put another ground here. You can do yours a lot better than mine. I don't know why. I'm trying to do this in a simple way that's slightly different than what's shown, but kind of messing it up a little bit here. Well, whatever, that's fine. That's close enough. Analog ground is grounded. The band gap is covered. Now we have this voltage divider. What's this voltage divider here? Well, we talked about when you're, basically this transistor and these two resistors, these are used to produce a LDO linear regulator. So this chip actually has a controller which will generate a nice smooth voltage to drive the load cell with. But to do so, it needs a set of feedback resistors and a transistor, and this is exactly what we talked about with the linear regulator. The linear regulator just uses a transistor to burn off voltage. The way it knows what voltage it's producing is with a voltage divider. So it's using a voltage divider to make this voltage smaller than what's actually here. It's feeding back to a constant voltage. So let's put this, let's put this transistor in there first. So S8550. So it turns out I got this look at sent items. Don't look at my emails, please. Don't look at my emails. So this is the parts I ordered for the class from Rezo. So these are the parts I ordered for all of you. These are what we've got. I just want to make sure we have the right one. So MMB, was this it? MMBT. Is it BT? S8550. Pretty sure I bought these. Maybe I copied what DigiKey did. Uh-oh. MMBT 4430. If you're probably seeing it and I'm just losing my mind here. PNP, this should be right. Oh yeah, MMBT, jeez, MMBT 440. Okay, this is it. So this is the part that we actually bought. So C78864, you obviously don't have this email, but I'm going to copy that. And then I'm going to go back to our software. And I'm going to say library. And I'm going to search for the actual part. That's C78864. That should directly give us the part that I bought. That's a good way to know that it's the actual part that I bought. Place that. So for now, we'll just rotate this, get it over here. I got to go back and see exactly how DigiKey did this. So the arrow side was connected. So VCC was connected to the arrow side. The gate was connected to base. So let's keep rotating this. So VCC, I'll take that. Control C, Control V. VCC connected to the arrow side. The base is connected here. Okay. And then that other side connects to AVDD. And I can already tell I'm going to have to move some stuff because I screwed myself here. Yeah, there's definitely a good reason why they did it a different way. So let's just get these out of the way. Okay. Okay. So then we have this inductor here. So odds are this inductor is actually a ferrite bead based on what it is. It's listed as an inductor. A ferrite bead is slightly different than an inductor. It does have inductance, but the idea of a ferrite bead is you're trying to choke high frequency noise. So an inductor does that in general. An inductor resists a rapid change in current. And so if you're using one deliberately to absorb high frequencies, switching noises, all sorts of messy stuff you don't intend. In this case, we're trying to generate a voltage supply for a strain gauge bridge. And we want that voltage to be dead steady smooth. It should be pure DC. There should be no AC. So they're putting this inductor and these capacitors here as a way to really filter that out. And so if we look at, we can see what I bought. What I bought for the inductor was, and this is a good way to go, just go with what I bought. So 3.3 microhenry inductor. Is that right? Yeah, 3.3 microhenry, okay. 3.3 microhenry inductor. This is the part. I'll hit Control C. Go to Easy EDA. Library. Oh gosh. Oh gosh. Okay, so I don't see the part show up here, and I actually remember doing this when I did this. So, so let's just go back to LCSC. And we'll type in our part. So this is the part that we have. Now the package is 1206. So it's a 3.3 microhenry inductor. It's a 1206 package. That means that the footprint is going to be 0.12 inches by 0.06 inches. And all that matters is, we can look at the data sheet for this. And, they can show the actual size of the inductor. It looks like they don't show a footprint here. But all that matters is that we get an inductor with a footprint that this will fit on. So just 1206 might be hard to find for an inductor, but 1208 would work. So 1208 footprint would be a little bit wider than 1206, but it should still work. Let's just find, just to speed ourselves along, let's find an inductor. It's about 3.3 microhenries. That's a 1206 or 1208. So 3.3, let's just see if that'll help us find it. Okay. So inductor SMD is what we wanted, 3.3. Now the question is the footprint going to be what we want? Well, this could be tough. Okay, so L0805, that's not what we want. We want 1206, right? 1210, that should work. It's going to be a little wide, but it should work. You know what, maybe we can just go back to DigiKey and find one. Here's what's fun sometimes. Go to the package, go to 1206, and click apply. And then see which ones are most available. And then steal that one. Sorry. This is how the sausage gets made. Okay, so let's try to do LCSC part number. Let's see if this one's in the library, because we know this is a 1206 footprint, or it should be a 1206 footprint. It looks the same to me. Interesting. A lot of results for that. Okay, let's go back. Okay, well, that looks right. 1206 extended part. Okay. Yeah, and it looks like this is a bigger inductance than what we have, but as long as the footprint's right, it'll be okay. So for now, we'll just use this. Let's just make sure they're all parts that are available. And we'll just, the footprint looks right. So we'll just go place. Okay. So we want that inductor here-ish. Let's give ourselves a little bit of space. Go back to our data sheet. So that inductor gets wired to AVDD through here. AVDD, okay. And then here is where that divider shows up. So we have a voltage divider, 20K and an 8.2K. Let's just copy what SparkFun does. We know it works, so we'll just use their thing. 20K, 8.2K. So the biggest thing is all of our resistors are 0603, so we really just want 0603 resistors. But let's find 0603. We should be able to find 0603 in a 20K and an 8.2K. Let's do 20K. So these are all 20 kilo ohm resistors. Let's find 0603. That looks right. Okay, who makes it? Yagio, they're a good company. So let's do place, rotate it. Yeah, I can already tell we're going to run out of a lot of, so this is going to be a mess. Let's put it over here for now. Escape. And then an 8.2K. Now resistors are, there's standard resistor value, so you can't get any old resistor value. You know, an 8.2K is one of the standard ones, but you know, a lot of students they'll do a calculation and they'll say, oh, I need an 8.257 ohm resistor. You can't necessarily buy that, or if you can buy it, it's possibly very expensive. So a lot of times with resistors, you're limited to the standard ones. 8.2K, 0603. Yeah, these are all fine. Oh, there's a Yagio one. 8.2K. Nope, it's 0402. Oh, see, these are real tiny. 0201. You don't want to play games with that stuff. 06. We'll just do this. 0602. 8 points. Okay. Okay. And then the bottom side of this divider has to be grounded. Okay, so now once again, I didn't leave myself enough space. So what we're going to do is we're going to take this resistor, we're going to move it up, and then, yeah, so we just made a connection we did not want to make. So by dragging that little ball showed up here. So I dragged the wire over this connection. The software thought I'd made a connection. Be very careful. That's why you don't really want wires overlapping ever, because if you get wires overlapping, it's very easy to accidentally mess those up. Okay, so we're going to move this up here. Hit escape. Select all that. Select all that. Move this over to here. It's already getting kind of messy. Okay, we can move this over here just for sanity's sake. And then we will run that wire here. Okay. So wire between the resistors went to VFB, top side of the divider went to the side of the inductor, bottom side went to ground. Sanity check. Middle went to VFB, bottom side went to ground, top side went to the inductor. All correct. Okay, then on this side, the capacitors, a 10 microfarad and a 0.1 microfarad. So the 10 microfarad's weird. 10 microfarad's big, and if you look at the SparkFun one, SparkFun has these big old whoppers for 10 microfarads. That's what I did too. I just copied the capacitors that they use. So if we want to see what those are, we can go to 10 microfarad. So they're 1206, big old capacitors. Let's find these, copy it, and then we'll go to library. Nope. Interesting. Did that do what I was trying to do? I don't know. Okay, now I found it. Quick place. Put that capacitor here-ish. Now we also, I just know we want another one here, so I'm just going to move that over there. Yeah, so I'll move it over there. So if we go back to, so what was that capacitor? That was this 10 microfarad here. SparkFun, not in addition to that 10 microfarad, they also do a 0.1 microfarad. Now this is interesting. A lot of students have questions about why the hell would you, if you have a 10 microfarad, put a little tiny 0.1 microfarad here? Because what are you doing? Capacitors in parallel add, that's 10.1 microfarads. Who cares? 10 versus 10.1, these are only 20% accurate. Who the hell cares about 0.1 microfarads? The reason they do this, the reason they put a small capacitor in a big one, is because the dirty secret with capacitors is big capacitors normally have very bad frequency response. That is to say, to a high frequency signal, this 10 microfarad capacitor would not appear to be 10 microfarads. Why is that? Because when you make really big capacitances, the way they do it is they have lots of large planes of metal with a very thin insulator between them. So to actually function as the full 10 microfarads, electrons have to get all the way to the back end of the capacitor through that resistive metal, get up to the surface of that oxide layer, and find a matching pair of charges on the other side. And it, depending on how you structure your capacitor, you know, those charged particles can't make it there that fast. Even if they're electrons, they can't necessarily make it all the way over there very quickly because there's capacitance, there's resistance in the metal. In cases of like electrolytic capacitors, you're not even using electrons, you're using ions in a liquid, which move very slowly compared to electrons. So a lot of capacitors have bad frequency response. They're putting a second capacitor here so that this thing filters out not only low frequencies with the 10 microfarads, but so it also filters out high frequencies. So we'll do the same thing. So we'll find a capacitor. Actually, we already have a 0.1 microfarad, right? We use that one here. So let's hit that, Control-C, Control-V. Hit that like that. And then we'll wire these up. And then we have to have grounds on both sides here. All right. Now, again, if it's getting a little messy, we can move the... Okay, so it doesn't quite look like SparkFun's, right? But it's the same thing. So we got this divider, this capacitor, this. So all of this is taken care of over here. Now it's basically just the connectors. Okay. So here's the thing with the connector on this side. You can build it, if you want to build your design exactly like this, you can do this with a 5-pin connector. The SparkFun one uses a 5-pin connector for E plus E minus. That's the excitation. That's the oh boy, I missed the data sheet here. Yeah, that's the here. So the top and the bottom of the load cell is the excitation. And then they have A plus and A minus. Those are the signals on the side. Those are the differential signals across the strain gauge, which those are the things that feed into our amplifier over here. The problem is the strain gauge that so this is set up for a full bridge strain gauge. The problem is the strain gauges that we're using are not a full bridge. The strain gauges that we're using are a half bridge. So they have the excitation would come into this, would go out to the strain gauge. The strain gauge would provide these two resistors here, but that's it. Then the strain gauge would provide these two signals here. So on our circuit boards, we have to add the resistors for the bottom half of the strain gauge. We have to add these resistors to the actual PCB. That's not something that's part of... Now, we could have them be external. We could wire them up. We could do it just like the SparkFun one, wire the resistors externally, but we'll do them on board. So we basically have to build this bottom half of the strain gauge amplifier. We have to build that on the PCB. So what I did is I bought precision resistors. So I had to buy... that's not it. I had to buy... Yeah, so this is a 0.1% resistor here. So this is an 0805 0.1% resistor. I have two different sizes depending on whether you're using a 350 ohm or a 1000 ohm strain gauge. Let's just do one of these though. So we have to copy this. Okay, so we did find the part. So we're gonna so these are the resistors that for us we have to build the bottom half of the strain gauge. I'm right clicking to pan back and forth. I'm doing a right click. So we're gonna put, so this is the bottom half of the strain gauge. So we have to have one resistor on each one of these channels. So we'll do one here and one here. These are both gonna be grounded. Let's just, for clarity's sake, just so it's clear that these are the bottom half of a bridge, we're gonna connect them both to ground. So those resistors have to be okay. So we had to build the bottom. So basically now what's going out to our strain gauge is we have power going out to our strain gauge here. And we're gonna have a connection to the top half of the bridge, which has to be here and here. So we have to connect these signals to the top half of the bridge, and we have to get excitation. We don't need the shield or the other wires. So technically we can use a 3-pin connector. If you don't want to do this, if you want to give yourself a connection exactly like what SparkFun did, that's fine too. But let's go back here. So to get a connector like this, we go to library and we say male header. We'll try to find a 3-pin connector. So 1x 6p is how they label it. So let's do 1x 3p. Well, okay. Let's do this another way. Let's go to LCSC. And we'll say 1x 3p. So these should be pin headers, and this looks like what we want. This looks exactly like what we want. So what we'll do is we'll take the LCSC part number, and actually sometimes it's best to first sort by availability. Yeah, let's go with this one. It's much more likely to be something we can find. Let's try to find that. Yep, there we go. Rotate this so it shows up like that. Okay. Hit escape. Okay, so now what we need is, so the wires we need off our board is we need a connection to power. We need a connection to one side of the bridge. And we need a connection to the other side of the bridge, which there's lots of ways just to avoid crossing wires, I'm going to do it like this. Okay. Does it matter which side goes where? Not really, because we have to physically wire these anyway. We have to run wires from the strain gauge to these pin headers. So if we have to switch the wires, we have to. But also, a strain gauge amplifier is just a differential measurement. So if you switch the two wires, your signal is just going to be big and negative instead of big and positive. It's just going to shift in a different direction, which is something you can fix in software, or you can just switch the wires. It doesn't really matter. Okay, so that should be fine for that. This is getting messy. This is messier than the one that I did beforehand. Okay, let's look at the other side of the data sheet. Let's go back to the SparkFun data sheet. So all of these capacitors floating off here in space. These are decoupling capacitors for the power supply. So this makes sure you have a nice clean power supply coming into the PCB. A lot of times if you're powering a PCB from an external source, that voltage supply has to run through a wire. That wire has a bunch of resistance on it, and so you know if you have changes in current draw, it's going to cause a voltage drop. So the way we fix that is we put a big capacitor. These capacitors, decoupling capacitors, are just like having a water tower in a city, right? A water tower in a city stores water at a certain elevation, and it provides a nice constant supply, constant water pressure to a city. Versus if you had all your water pumped from one source in a state, you know, as you get peak water demand, as you start drawing water, you get water flow through that pipe down to the local city, and you're going to get pressure drop across that pipe as it flows. So instead, the solution is put water towers up in every single little town. That's what we're doing here with these capacitors. We're putting a little water tower up in every single town. So let's drop a couple of these. I already knew I was going to have to drop this 10 microfarad, so I did that. And then they say a couple 0.1s for decoupling. Now they have VCC and VDD. We just have one power supply. But who cares? Let's give ourselves a little extra. So let's take this, copy that, paste it here, paste it here. It never hurts to have extra capacitors. And then we're gonna, all of these are gonna be VCC. Oh, we gotta make sure we click the whole thing, not just the name. And I messed it up. Okay. Okay. And then we're going to ground the other sides of that. Okay. What else do we need? Well, now we need the connector that's connecting into our PCB. Let me pause really quickly, and we'll meet up a little bit later.